Welcome and good morning, everybody. It's my pleasure to introduce to you Holger Baumgardt, who is our speaker of today. And Holger is associate professor at the University of Queensland in Australia, and he's originally from Germany, and he got his PhD in Heidelberg. After that, he went through a few postdocs, if I remember, still in Germany, in Heidelberg and in Bonn, and then also in Tokyo and in Edinburgh in Scotland. And after that, he moved to Australia, and he has been there now for a while. Holger is one of the worldwide experts on, especially on globular clusters from different points of view, and both from the observational point of view and theoretical point of view. And he's really expert also on the dynamics of collisional stellar systems, also using collisional and body simulations. And related to this, of course, is also the topic of the seminar today, because he's going to talk about the presence of black holes in stellar systems, in small stellar systems like globular clusters and dwarf galaxies. And one thing I would like to say that this is also a special seminar also for the room in which the seminar takes place, because you know that the room is named after our colleague Antonio Sollima, and Holger has been collaborating with Antonio for a few years, and they have done a lot of interesting work together. So it's, I mean, a special speaker for also to remember Antonio. So please, yeah. Holger, okay. Thank you very much.
Yeah, okay, so welcome everybody. Today in my talk, I want to talk about the presence of massive black holes in stellar systems. And so that is work, as Carlo already mentioned, that I've done with...
Sorry, we should click on there, but I can't see it.
I think you have to do it.
You do it, but I can't see it on this.
Maybe you have to move, not for the presentation.
No.
No. You made it there. Made it through.
Okay.
Maybe if you go outside the presentation mode. No, nothing else.
I can leave again.
Yeah,
then you click on this
Yeah.
and this as well, and then you come back. There we go. Okay, thank you.
Okay, now it's better here. Yeah. Okay, so I want to talk about the work that I've done together with Antonio Sollima and other collaborators on the presence of massive black holes in stellar systems. Okay, and so basically the starting point or the motivation of our work is the well-known M-sigma relation. So which relates the mass of supermassive black holes in the centers of galaxies to either the total mass or the bulk mass of a galaxy or its velocity dispersion. So, I mean, that is a relation which is very well established for major galaxies. And I mean, it is known that basically all large galaxies like the Milky Way or more massive have central supermassive black holes of masses of something like 10 to the 6 solar masses up to almost 10 to the 10 solar masses. But I mean, this M-sigma relation then also raises several questions. And one of them is, of course, so how does this relation scale towards lower mass? And that is also an interesting question, because that is also related to the question of how these supermassive black holes have actually formed. So did they form in one go with masses of 10 to the 6 solar masses already? Or did they maybe form from the mergers of or the slow growth of smaller mass black holes? In which case one would probably expect that this relation continues to also much smaller black holes. And so, and therefore, that is something that we try to answer. So, can we find smaller mass black holes? And then, so based on the M sigma relation, so then the question is, okay, if you want to find smaller mass black holes, so where should you look at? And I mean, for that, it is interesting to plot all the known stellar systems in a diagram which has either the luminosity or the mass of the stellar system on the x-axis and the size of the system on the y-axis. And then what one gets is basically such a distribution. So, I mean, the massive galaxies or the large galaxies, they occupy the upper right-hand corner. They are very massive and they're also very extended. And then when you go towards smaller, so fainter systems and also more compact systems, then you have various other systems. So the dwarf spheroidal galaxies up here, the so-called ultra-compact dwarf galaxies here, and finally star clusters like the globular clusters in the lower left-hand corner. So these are the faintest and also most compact systems. So the evidence for supermassive black holes, they are basically only in the upper right-hand corner, so massive galaxies. But possibly also some of the other systems do have black holes. And I mean, in my talk, I want to talk about two different types of systems. So first are the so-called ultra-compact dwarf galaxies, so which are sitting here. And then I want to talk about globular clusters sitting down here. Okay, but let's come first to ultra-compact dwarf galaxies. So what are ultra-compact dwarf galaxies? Well, basically, these UCDs, they were discovered about 20 years ago in surveys of nearby galaxy clusters, so like Virgo or Fornax. So observationally, they turn out to have masses of something like 10 to the 7 up to a few times 10 to the 8 solar masses, so significantly more massive than a typical globular cluster. And sizes are also in the range of a few tens up to 100 parsec. So, I mean, initially it was actually quite puzzling to astronomers to understand where these ultra-compact dwarf galaxies are actually coming from. And there were initially two ideas. So one idea was connecting UCDs to globular clusters. So the idea is either that UCDs are simply the high mass end of the globular cluster distribution. And that is possible because when you look, there seems to be a constant transition from globular clusters to UCDs. But I mean, the other idea was basically that was connecting UCDs to galaxies. And here the idea was, I mean, if you're looking at galaxy clusters, then of course you have a very high density of galaxies, and therefore you will have lots of encounters between galaxies. And I mean, while usually, I mean, an encounter between two galaxies leads to the merger of the two galaxies. So you form one galaxy out of two smaller ones. There's of course also the possibility that, I mean, if the impact parameter is a little bit larger, then you do not get a direct merger, but instead the smaller galaxy will be tidally disrupted. But maybe the center of this galaxy, which is the most massive and highest density part of a galaxy, that might survive this encounter. And then the center, so the nucleus of the galaxy, is moving around as an isolated nucleus and will then appear to an observer as a UCD. So therefore, I mean, there are two different pathways of forming UCDs possibly. But of course, if UCDs come from the galaxy side, then, I mean, one natural prediction, which one would expect, is that UCDs also contain supermassive black holes. And so therefore, that makes UCDs really like a prime place to look for supermassive black holes, and possibly also smaller ones. And so therefore, that is one thing that we have done. So, I mean, the first target galaxy or UCD that we were looking at is called M60 UCD1. So that is basically the brightest UCD, which one can find around the galaxy M60, which is one of the brightest galaxies in the Virgo cluster. So observationally, that is already quite an interesting system because, I mean, one can determine an absolute magnitude of something like -14. So that corresponds with a standard mass to light ratio to a mass of about 300 million solar masses. So it's really an extremely massive system. And interestingly also, that UCD in its center hosts an accreting X-ray source, which could already point to an accreting massive black hole. And so therefore, I mean, from the X-ray source itself, it's not clear if it is a stellar mass one or a supermassive black hole. So, and therefore we obtained IFU kinematics for this UCD. So you can see the results here. So on the left-hand side, that shows the rotation signal. So I mean that UCD is rotating. And here on the right-hand side, you see the velocity dispersion. And here the interesting thing is, if one looks at the velocity dispersion shows a very strong increase if you go towards the center. So in the outer parts, it's something like 40 kilometers per second. And in the center, the velocity dispersion reaches about 100 kilometers per second. So it's an extremely strong increase. And then if one does some dynamically modeling, so assuming that, I mean, the stars are everything which creates the mass in the UCD, and then adding various central supermassive black holes to the UCD. So then one can try to reproduce this increase, and the results are shown here. So that is just a grid which has the stellar mass to light ratio on the x-axis and the central black hole mass on the y-axis. And so what we find is that in this UCD, you do need a supermassive black hole of something like 15 times 10 to the 7 solar masses, 10 times 10 to the 6 solar masses, in order to explain the central increase of the velocities. And so that also with pretty high confidence. So therefore, our result for M60 UCD1 was it has a massive black hole of something 2 times 10 to the 7 solar masses, and the total mass based on the kinematical modeling is something like 2 times 10 to the 8 solar masses. So that means the central supermassive black hole makes up 10% of the total mass of the UCD. So I mean that is quite enormous. But on the other hand, if you think that this UCD might have formed by the tidal stripping of a larger galaxy, I mean, these values or that ratio, that is quite typical what you also see, say, for the nuclear cluster in the Milky Way. So, I mean, in the nuclear cluster in the Milky Way has something like 30 million solar masses, and it hosts a central black hole of something like 4 million solar masses. So therefore, that system is kind of a scaled up version of what we see in our Milky Way in the center. Yeah, and then after M60 UCD1, I mean, we were also looking at a few other of these UCDs. And I mean, we always found a pretty similar picture. So, I mean, again, one can measure the velocity dispersion as a function of distance to the center. And in those systems that we had to look at, we always see this very strong rise of the velocity dispersion if you go into the center. And again, if one does some kinematical modeling, so these red models here, these are simple mass follows light models without adding some central mass. And so there, as you can see, I mean, the increase that you expect is far less than the observational one. So again, I mean, there is additional mass in the center, and the most reasonable assumption is that this is a central supermassive black hole. And I mean, that way we also found, again, I mean, you need quite substantially large black holes in order to explain this increase.
Sorry, Holger, do you have any idea what is the linear scale of the radius you are sampling with the
I think at Virgo distance, 1 arc second is about 70 parsec. So you are looking at something like 35 parsec or so on the x-axis. Yeah, so I mean, it is, yeah, I mean, they're a bit larger than a typical globular cluster also.
So the range of influence of the black hole is pretty large.
Yeah, I mean, it is 10% of the mass of the whole stellar system, so that creates quite some significant influence. Yeah, so I mean, therefore, I mean, we really found these supermassive black holes in the number of these UCDs. And so, I mean, therefore, UCDs are also one of the places which one can probably assume quite safely. So a large number of them will have supermassive black holes. And what that also means is probably that this formation channel, assuming that UCDs are formed from the tidal stripping of larger galaxies, is probably a reasonable one. There will be a substantial population of these UCDs which have exactly formed this way. Yeah, okay, so I mean, that was quite good. But I mean, one problem that we have is when you look at the black holes that we found, I mean, these are all still supermassive black holes. They typically have a few million solar masses. So, I mean, our initial aim was really to push towards lower mass systems, so below 1 million solar masses. So basically into the so-called intermediate mass black hole regime. But that was something that for the UCDs, we have not found. And so therefore, we still need to look at basically smaller systems and see if they have intermediate mass black holes. And that brings me to the globular class.
Holger, I have a question
Yeah.
about this modeling. Are you assuming that the mass to light ratio of the stellar population is just dependent of position, or
Yeah,
are you?
yeah. I mean, for the stellar population, we assume the constant mass to light ratio. But I mean, that was at least partially also justified because, for example, we do not see strong or any, say, color gradients. So, I mean, therefore, that is probably reasonable. The relaxation times are also relatively long. So, I mean, sure, these systems probably also contain stellar mass black holes, but I mean, with relaxation times of hundreds of millions or billions of years, it is quite unlikely they're not going to make it into the center. And you would typically also not expect that, say, stellar mass black holes have such a large mass fraction of the system. They don't contain typically 10% of the mass of the system. So therefore, that should be fine.
Is this tidal stripping, wouldn't move it off the relationship by making it smaller?
Yeah, so okay, I haven't shown the UCDs here, our mass determinations, but I have on the very final slide. When I summarize everything, I have a plot. But yeah, I mean, it's true. Okay, or it depends a bit. I mean, if you would put on the x-axis the total mass of the system, then the UCDs are completely off because they are just a former remnant of a 100 times more massive galaxy or so. So I mean, yeah, they in terms of mass, they would not follow the M sigma relation anymore. Definitely not. But I mean, in terms of velocity dispersion, it's actually not too bad because I mean the velocity dispersion of a UCD is 50 kilometers per second, which is typically also of a bulge of a galaxy also. Yeah. Okay. Yeah. So if there are no more questions, then so let's move on to globular clusters. So I mean, could there be massive black holes? So then maybe more, not in the million solar mass range, but maybe in the range of 10,000 or so of solar masses, so intermediate mass black holes. Could they exist in globular clusters? Well, in principle, that is not such a strange assumption, because they say when you look in the Milky Way, I mean, there are globular clusters which are actually not really globular clusters, but really more nuclei of dwarf galaxies. So, I mean, the most famous example is the globular cluster M54, which observationally sits right at the center of the Sagittarius dwarf galaxy. So again, if there are massive black holes in galaxies, and if they are also in dwarf galaxies, then I mean that such a black hole would also be sitting in M50. And there are also other globular clusters which are not the centers of dwarf galaxies anymore, but which are speculated to have been the centers of former dwarf galaxies. And again, I mean, it is reasonable to assume they could contain massive black holes. Yeah, so it's definitely a good idea to have a look. And I mean, the one cluster that we did have a look at, and I mean, which is also a cluster that Antonio has done a lot of work about, is Omega Centauri. So observationally, Omega Centauri is the most massive globular cluster in the Milky Way. So it has a mass of about 3.5 million solar masses. And what makes Omega Centauri also interesting is that if you have a detailed look at the stars in Omega Centauri, so you measure their metallicities, for example, then what one sees is that, I mean, it does not look like Omega Centauri really formed in one go. I mean, in a typical globular cluster, star formation is basically a one-off event. You form all stars from a giant molecular cloud, then the gas is dispersed, and there is no more star formation. But in Omega Cent, it seems that the cluster really has a very long, so say about a giga-year, long extended star formation history. And the second thing that was also something that Antonio found was that if one looks at the metallicity distribution of the stars, there's also a large spread. So the lowest metallicity stars have something in Fe over H of about -2 or so, and then it goes all the way almost up to solar metallicity. Yeah, and that was also something which in a recent paper by Nichai et al. Based on mu spectroscopy, they also showed. So, I mean, here you see the metallicities of the stars color-coded, and I mean, color magnitude diagram. So, I mean, there's a very large metallicity spread. Observationally, what one also sees is that the kinematics of these different metallicity distributions, they're also not the same. So, I mean, therefore, it is quite likely that Omega Centauri is actually not a simple globular cluster, but maybe, again, a nucleus of a former dwarf galaxy, where you had constant in-spiral of gas into the center, and you formed a new generation of stars over quite an extended period until the galaxy was disrupted and no more star formation. But again, as a nucleus of a dwarf galaxy, that of course makes Omega Cen a prime target to look for an intermediate mass black hole. Yeah, and that is something that people have done already for quite some time. So the first papers were done by Noyola et al. In 2008. So what they did is, or what I do here, also in my plots is, so you basically, again, you model the surface density profile of the cluster, and then apply a model and see how that model fits the observed velocity dispersion profile of the cluster. And one thing that one immediately notice is, if one assumes, okay, mass follows light, so the visible stars is basically everything which creates the mass in Omega Centauri, then, I mean, one gets basically the red curve. So, I mean, in the outer parts, one can, again, start to confirm or follow that observed increase of the velocity dispersion. But as soon as one gets into the center, such a mass follows light profile simply predicts too low velocities. So the observed velocities are higher than the prediction of this model. And then one can again start to throw in massive black holes of various masses and see, so by how much do I have to increase the mass in the center in order to predict the observed velocities. And what one finds is, okay, I mean, that is possible with an intermediate mass black hole of something like 50,000 solar masses. And so therefore, there had already been claims in the literature about 15 years ago that Omega Centauri does contain an intermediate mass black hole. But unfortunately, in the case of Omega Centauri, it is actually not that simple. Because if you look at Omega Centauri and compare it with the other globular clusters in the Milky Way, so one can, for example, make a plot which shows the central escape velocity, so the speed that you need in order to be able to leave the cluster, versus the relaxation time of the cluster. So that is the time scale on which stars do change their orbits and start to dynamically influence each other. Then what one sees is that Omega Centauri is actually occupying a relatively unique spot among the globular clusters of the Milky Way. So Omega Centauri is not the cluster which has the highest escape velocity. So there are other clusters like M54 or NGC 6388, which have a slightly higher escape velocity from the center. And Omega Centauri is also not the cluster with the longest relaxation time. So that is NGC 2419. But what is unique about Omega Centauri is that this is a cluster which actually has both a very high central escape velocity and a very large relaxation time. And so then one can ask, okay, so why is that special? Well, that starts to get special when you think about stellar mass. Because when you look at Omega Centauri and you look when it formed, I mean, when it formed, it probably formed with a mass function which was populated from the lowest masses, so 0.1 solar masses, all the way to the highest masses, so 100 solar masses. And I mean, then when you any star which formed with more than 15 solar masses will have formed a stellar mass very early. So now there are two processes which can eject stellar mass black holes from star cluster. So the first is natal kicks. So if stellar mass black holes formed by supernova explosions, and the supernova explosion is not perfectly symmetric, then the black hole which forms out of the supernova will get a kick. And these kicks, they are probably of the order of something like 50, 100, or 200 kilometers per second. But then, given that the escape velocity of Omega Centauri is so high, you would expect, okay, Omega Centauri together with a few other clusters here on the right hand, and they should be able, or there are black holes which form in them, they should largely be able to remain. And then the second process which can eject stellar mass black holes from globular clusters. So these are basically dynamical encounters. The black holes will spiral into the center, and then they will start to approach each other. They form binaries and then throw each other out. So that is the second way how a star cluster can get rid of stellar mass black holes. But again, since the relaxation time of Omega Centauri is so long, this is again a very inefficient process. So therefore, when you look at all the globular clusters in the Milky Way and you ask which cluster should be the one which probably still has the highest fraction of the stellar mass black holes which formed initially remaining in it, then this is Omega Cent. And so therefore, the stellar mass black holes, that is something which needs to be taken into account in the model. Yeah, and so that was something that I did back in 2019 together with Antonio. So, in addition to an intermediate mass black hole, we also looked at models which retain a large fraction of the stellar mass black holes. And so, here the result is shown in red. And as you can see, these models, they can actually perfectly accurately also predict the velocity dispersion. So therefore, our conclusion was back at that time, the question is totally open. Does Omega Centauri have an intermediate mass black hole or not? Is undecidable back 5 years ago. Yeah, so, what do you do? We still want to know, is there one or not? The data that we had back in the day was not enough. So what do you need? You need new data. Okay, and that was then something where Maximilian Heberle and Nadine Neumeier came in, because their idea was, okay, let's go back and have a look at HST data. Because one thing that is unique about Omega Centauri is also, it is an interesting science target, but Omega Centauri is also an interesting engineering target. Because, the HST is already up in space and flying since 30 years. And of course, the detectors in the HST, they age. And so therefore, one thing that the engineers who are running the telescope have to do is they have to regularly check. So how is the telescope still working? So that you can get useful science out of it. And so the way they do it is every few months, the HST is passing by Omega Centauri and taking an image of the center. And then what engineers do is they just compare the newest image with the older ones and see how much has the telescope changed. So therefore, in the HST archive, Omega Centauri has tons of observations, hundreds of them, which basically nobody really had a look at. That was for the engineers, not for the scientists. But Max and Nadine's idea was to take these images and do astrometry. So measure the positions of stars on these images and then derive proper motions of these stars. Because you get a 20-year baseline, so therefore you can really obtain very accurate proper motions. Yeah, and so that is what they basically did. So they determined a new catalog of proper motions in Omega Centauri. And that was, of course, a large increase over existing catalogs. So for example, down here, that is shown, this is the number of stars which you can find in Gaia in the central 20 arc seconds. Then there are older HST-based catalogs by, for example, Bellini et al., which are, of course, much deeper already than Gaia, but this is their newest work. And as you can see, the number of stars has significantly increased. And of course, with more stars, you can also push more into the center of Omega Centauri. Yeah, and so that is something that they have done. So this year again, shows the result for the newest velocity dispersion profile. So that is, again, first HST data, and secondly, also the new Muse data by Nichai et al. So as you can see, okay, I mean, for the innermost data points, we start to see an increase. And that increase is higher than what the best model without an intermediate mass black hole can allow. So even a cluster of stellar mass black holes, these stellar mass black holes, they will be distributed in the core. So they are not going to create a rise in the very center. So, I mean, here you can already see the data starts to deviate from the model without an intermediate mass black hole. Or for, I mean, it is just in the innermost data point, so not that significant. But another thing that they also found was that, I mean, in the center of Omega Centauri, there are actually about 6 stars which are moving with extremely high velocities. So, I mean, the velocities go from something like 65 kilometers per second all the way up to 113 kilometers per second for the fastest star. And that is larger than the nominal escape velocity from the center, which is something like 65 or 62 kilometers per second. So there is a population of stars which is significantly faster than the escape velocity. So given that there are so many of them, I mean, this is unlikely that these stars are created dynamically. And we just see them, okay, they just, you had a star on encounter, and I mean, one star got ejected with a high velocity, but we have too many of them. If Omega Centauri would try to maintain 6 too fast stars which are leaving, over Hubble time, the cluster would not be there anymore. So, I mean, this cannot be due to dynamical creation. It can also not be background stars, because again, there are far too many of them. And it also cannot be stars which are, say, moving around another star, say a stellar mass black hole, because with that 20-year baseline and these velocities, we should have started to see the curvature of the orbits. So therefore, the only viable explanation for these fast stars is really that there is a massive central black hole, which makes these stars move around. Because with these velocities and, say, a 10,000 solar mass black hole, over 20 years, the orbit could still be a straight orbit. It would take longer to start to see the curvature. Yeah, and so therefore, I mean, our conclusion is, yeah, that, I mean, these fast stars, this is basically what proves that there is a massive black hole in Omega Centauri. So again, I mean, that is another plot which just shows the measured 2D velocities of the stars. And here's the nominal escape velocity. And so here are these very fast stars. Yeah, so at the moment, we don't have a very good measurement for the mass of the central black hole just from the fast stars. So that requires some more modeling, but we are working to it. I mean, the minimum mass that we have for the central black hole is something like 8,000 solar masses. That is, if you put the black hole in the most favorable position to explain these fast stars, and you put the fast stars as close as possible to that central black hole. But I mean, most likely mass is maybe something like around 20,000 solar masses. So therefore, I mean, it's not a stellar mass black hole. It's also not a supermassive black hole. It is really an intermediate mass black hole. And with that, also the first which has been found. Yep. Okay, and that's basically already the end of my talk. So I mean, this final slide.
Okay, just one. Curiosity.
So
Do you have any line of sight final velocities?
no, we are trying to get them. I mean, with Muse, it is possible to get them. So we are already since a year and a half writing the same proposal again and again and submitting it to ISO. But so far not successful, but hopefully.
If I remember correctly, these stars are pretty faint, so
Yeah.
Muse enough to get them.
I think for the brighter ones, you can get the velocities with Muse.
Good luck.
Yeah, yeah. So hopefully it gets. I mean, one thing that is interesting is we have a JWST proposal for it, and I mean, if that is accepted, and I mean, if the intermediate mass black hole interpretation is correct, then most likely we should start to see the curvature of the orbit. So at the moment, for one star, it is a 2 sigma effect, so still not significant, but with one more data point and with JWST, we should be able to start to see the curvature. And that will be interesting because, I mean, after the supermassive black hole in the galactic center, so that is only the second case where you can really see part of node of the star.
Will Gaia DR4 help in that too, in the acceleration?
No chance. I mean, these are also 24 magnitude stars, so they are too faint for Gaia, and it's probably also too crowded. So even with the newest release, I think you can't push not even to 20 in the very center. It's just stars everywhere.
Omega Cent is one of the few fields where Gaia also provides images.
Yeah, I mean, they had that special release between DR4 and DR3 and DR4, that FPR release.
Exactly.
I mean, that I showed that before. I mean, that has increased the number of stars inside Omega Centauri, which have some measured astrometry, but I mean, it's, yeah, so that is this FPR, and that is our, so
it's not faint enough.
not comparable.
Okay.
Yeah. Okay, so I mean, that plot here basically summarizes what we have found so far. So I mean, this is as a function of either the globular cluster or the UCD mass. And that is the mass of the SMBH or IMBH that we have found. So up here, these are the UCDs, which have mass around 10 to the 8 solar masses and few million solar mass black holes. Here are a few non-detections or upper limits, which I haven't talked about. And I mean, down here is Omega Centauri. So I mean, it seems to lie on a continuation sequence. And I mean, if you would plot more galaxies or galactic nuclei here with their detected masses, then that would probably also be somewhere here. And I mean, here, what I also show, the black dots, these are data points from the Eagle simulation. So, I mean, in Eagle, they started to throw in black holes with 2 × 10⁵ solar masses, and then had some description of how they can grow. Clearly, I mean, up here, it works quite well. But I mean, if this IMBH and Omega Centauri is really related to these supermassive black holes, then I mean, the black holes start at lower masses. But I mean, of course, you probably also want to have more systems down here to really understand what's going on. Yeah, okay, so thanks for your attention.
Hello? 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 Can you hear me?
Yeah.
Thank you very much, Holger.
Thank you for this extremely interesting presentation. You are in this moment in Bologna.
Yeah.
If you could visit us in Pescara, we could discuss this matter very much, because they are very interesting points. The most interesting point I found